Algebra 2, Section 11.3, Geometric Sequences. Starting with a definition of geometric sequence, it's a sequence of numbers or a list of numbers that increases or decreases by the same multiplier. We've seen this, we saw examples of these in Section 11.1. The name of that multiplier that I'm talking about is called common ratio. This lesson will seem to mirror the previous lesson, Section 11.2, with arithmetic sequences. This is just a different kind of sequence. So on that lesson, I had two ways to model. Once again, there are two ways to model a geometric sequence. Now they are different, right? This isn't just exactly the same. Obviously, a geometric sequence is different from arithmetic, but the way we model it is the same way in that there will be at least two lines, okay? And for Algebra 2, there will be exactly two lines on any problem we give you. So you need to identify what the first term is, and then you want to identify what every other term is based on the previous term. And I think I mentioned in the last lesson, if there's one thing that students have a hard time with, it's this right here, that a sub n minus 1 just stands for the previous term, okay? So if I'm on the 10th term, I need to plug the 9th term in here. And that 9th term times r, by the way, r is the common ratio. The common ratio is the r value that you find here and also here in the explicit formula. I don't want to leave those there, so I'm going to take them off, but that's the common ratio. That's the r. They picked r for ratio. You're just taking the previous term and multiplying it by r. Therefore, in the explicit formula, you take the first term and you multiply it by r a certain number of times. How many times? Well, n minus 1 times, okay? Because to multiply it by r one time would give you the second term. To multiply by r two times would give you the third term. So if we want, again, just pick a number. We want the 8th term. 8 minus 1 would be 7. That's how many times I want to raise r to that power, 7th power, to multiply by a1. That'll give me the 8th term. a1 is the first term, multiplied by r 7 more times to give me the 8th term. Okay. Okay, so an example to start. Is the given sequence geometric? If so, identify the common ratio. What you'll find is that in geometric sequences, they can alternate positive, negative. So don't take one glance and think, well, it can't be because positive, negative, positive, negative. That would be true for arithmetic. You can't have that for arithmetic sequences. But how do you get from 1 to negative 6 using a multiplier? That would be by multiplying by negative 6. How do you get from negative 6 to positive 36? Also by multiplying by negative 6. Same thing here. So in fact, this is a geometric sequence, and since it is, they say, if so, identify the common ratio. That number, negative 6, is the common ratio. The r value is negative 6. Okay? Now, let me just make this quick point. The common ratio is not the operation and the number. It's just the number. R is negative 6. It's not times negative 6. You shouldn't include that when we ask for the common ratio. It's just a number. It's a number that can be plugged in. You don't need to say times negative 6. What about this one? 2, 4, 6, 8. Well, to get from 2 to 4, you could multiply by 2. To get from 4 to 6, you do not multiply by 2. Okay? In fact, 2, 4, 6, 8 is an arithmetic sequence that's going up by 2 consistently. There is a common difference of 2. There is not a common ratio. Oh, by the way, I did want to make this point. Back on this example. Common ratio. Why is it a ratio? You know that a ratio is something that's a division problem. Well, it's a ratio because the current term, negative 216, divided by its previous term, 36, would give you negative 6. Also, 36 divided by negative 6 gives you negative 6. Negative 6 divided by 1 is negative 6. There's a ratio that you're getting when you divide the current term by the previous term, and since that was the same thing for each division problem that I attempted, which was all of them, every term divided by its previous term came out to the same thing. Well, it's common. It's alike. It's the same number. It's negative 6. So that's a common ratio. Next example. Suppose you have equipment that can enlarge a photo to 120% of its original size. A photo has a length of 10 centimeters. Find the length of the photo after 5 enlargements. Okay, now before we do the problem, I'll say again, after 5 enlargements would suggest you want the 6th number in the sequence. You have an original, and then you're going to enlarge it 5 times from the original. That would actually be the 6th one. And my strong recommendation for you on this is, on problems that are kind of real life, is to list out a couple of numbers, especially if you get stuck. If you get stuck, if you get lost, list out a couple of numbers. What are we starting with? A photo that is 10 centimeters. What if I take that 10 centimeters and I multiply it by 120% one time? You know that 120% is like multiplying by 1.2. Take 10, multiply by 1.2, you'll have 12. Take 12 and multiply by 1.2, you'll have 14.4. What I'm doing there is actually calculating things recursively, right? By multiplying it by 1.2 and then multiplying again by 1.2, I'm calculating over and over again recursively. In fact, I showed you how to do this on your calculator. And the next number would be 17.28. By the way, these have names. They are A1, A2, A3, A4. A5 would be 20.736. And A6 would be 24.8832. And that's what we're looking for, right? That's the answer that we're looking for, 24.8832. So that really isn't the way that they would have you to do this problem, but you certainly could. I wouldn't get mad at you for calculating the correct answer, but using a recursive method. And you get 24.8832. Now, let's write out the recursive and explicit formulas for this example. It's a rather short lesson. We have the time for this. There's only 3 examples total from the software here. A1 is 10. A sub n, is the previous term times the common ratio, and the common ratio is that multiplier that is 1.2. So this would be A sub n minus 1 times 1.2. Now, many students I know would rather have that 1.2 out front. That's perfectly fine. If you write your recursive formula like this, A sub n is equal to 1.2 times A sub n minus 1, that's totally fine. But again, are you getting it? This stands for the previous term. A sub n minus 1 just means the previous term, no matter what it is, right? Whether we're talking about the first and then the second term, or the second term and then its previous term, the first term, or we're talking about the 827th term, its previous term would be the 826th term. Okay? So that's explicit, that's recursive. And then the explicit formula would be A sub n is equal to the first term 10 times r, which was 1.2, to the n minus 1. And let's just go ahead and test that. Let's just make sure that what we're saying is correct. I wanted the 6th term in the sequence. If I plug a 6 in here, then on my calculator, I'm doing 10 times 1.2 to the 5th. And again, it gives me 24.8832. Same number. So find the length of the photo after 5 enlargements, 24.8832 centimeters. This came out to 24.8832 when I plugged in a 6. Okay? All right, back to the notes here. Something called a geometric mean. This is something different than an arithmetic mean. Arithmetic mean was just the way you've always calculated an average. Geometric mean is something different. The calculation is the square root of the product of the two numbers. In fact, full story is that if you were given 3 numbers and they wanted the geometric mean, you'd take the cube root of the product of all 3 numbers. If they gave you 10 numbers, you'd take the 10th root of the product of the 10 numbers. Okay, now we're not going to do that. In Algebra 2, we're going to stick to 2 numbers, but that is in fact the case, the way you calculate a geometric mean. So if I gave you 2 and 8, then you would take the square root of 2 times 8. 2 times 8 is 16. The square root of that would be 4. The geometric mean of 2 and 8 is 4. And the reason that's important is because in the homework you'll see problems like this. 3 blank 18.75. Okay? And you'll be told that this is a geometric sequence. Now, did you notice in that first example where I did 2 and 8, that if you did 2 plus 8 divided by 2, you'd get 5, right? The average of 2 and 8 is 5, but the geometric mean was 4. It was something different. And for that reason, you better not use the wrong calculation. When they say this is a geometric sequence, you're going to want to calculate the geometric mean. So to do that, you're going to want to take the square root of 3 times 18.75. You'll need your calculator for that, and that'll come out to 7.5. Now, one more small point about this. Remember that first example we did that was alternating positive, negative, positive, negative? That can happen here as well. So it could be the case that this is 7.5. It could also be negative 7.5. So you ought to put a plus or minus symbol in here as well. If the common ratio is, I guess it would be 2.5, right? 2.5. If it's positive 2.5, well then 3 times 2.5 would give you 7.5. If it's 3 times negative 2.5 would give you a negative 7.5. And I'm just going to double check that on my calculator. 3 times negative 2.5 gives me negative 7.5. And then if I multiply that one again, that number that's in my calculator again by negative 2.5, it does produce this 18.75 that was given. Okay. Now, if you want to pause to do the next one, just calculate it yourself. Go ahead. I'm just going to tell the answer here. Plus or minus 1,530. Find the geometric mean of 9,180 and 255. This one's going down, right? But it can go down as positive, 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 or it could go down as positive, negative, positive. The next one would be negative, positive, negative. And so it could be 1530, it could be negative 1530. Okay? And then second to last here is, what if we give you 3 blanks? If we give you 3 blanks, you want to find the middle one just as we did before. And the square root of 5 times 80 would be 20. 5 times 80 is 400, and the square root of 400 would be 20. And then I can look at just the first half, 5 blank 20, to find this number. And by the way, that 20 is not going to have a possibility of being negative, right? It's not ever going to go positive something negative something positive. It could simply go positive, 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 or positive, negative, positive, negative, positive. So this one could be plus or minus. This one should be plus or minus. And 5 times 20 is 100. Divide that in half, or not divide it in half. 5 times 20 is 100. Square root would be 10. So 5 plus or minus 10, positive 20, and then do the same thing here, would be 40. Okay, now just pause on that one. 5, 10, 20, 40, 80. Isn't that going up by a multiplier? And even if it's 5, negative 10, 20, negative 40, your multiplier would be the same number, but it would be negative. Okay, last example. Here's a real life example that will be relevant to you someday, probably. One day you'll purchase a home. A family purchased a home at $150,000. 2 years later, the home was valued at $159,135. I changed that number because the number they had there was ridiculous. It was so high. It was like a 12% per year growth. I brought this down to something that's a little bit more realistic. Anyway, if the value of the home is increasing geometrically, how much was the home worth after 1 year? Now, let me just tell you that values of homes do increase geometrically. They do not increase arithmetically. If you buy a $100,000 home today, and a year from now it's worth $101,000, it's not going to go up 102, 103, 104, and 105 like that. No, it's going to go up based on the previous value. Now, these are always subject to the economy and inflation, all that. So I'm not saying that it's, a guaranteed formula, but generally speaking, it's based on the previous value. And taxable value is certainly based on previous year's values. So anyway, what you would do is you'd take the square root of 150,000 times 159,135. And I had the answer here on my calculator, but I might have to recalculate that. Nope, there it is. 154,500. That's what it was worth after 1 year. Okay, so again, understand the question. You bought the house for this. We didn't know this value. The next year it was 159,135. You use the geometric mean to find this value right here. And it does turn out to be that the number that I used was 1.03, 3% growth. So 150,000 times 1.03 would bring you here, times 103 would bring you to the 159,135. All right, that's it. Thanks for watching, and good luck on your homework.